Whether you're frantically prepping for a final exam or you're just genuinely curious about the physics of everyday life, you are in the right place. Today, we're going to completely demystify the unseen mechanics of our universe. This explainer is built to give you the exact tools and the ultimate cheat codes you need to absolutely master both electrical circuits and electromagnetic radiation. So let's just dive right in.
Before we jump into all the formulas, the constants, and the complex circuit diagrams, we really need to pause and ask ourselves a pretty fundamental question. How do these two profound, completely invisible forces, electricity and light, secretly dictate practically every single aspect of our modern lives? From the device you're literally watching this on, right down to the heat we feel from the sun, it is all governed by these unseen rules.
Here is our quick game plan for today. We're hitting 1. The invisible forces around us. 2. Anatomy of electric circuits. 3. Series versus parallel pathways. 4. Cracking electromagnetic radiation. 5. The complete EM spectrum. And finally 6. Mastering the universal math.
All right, let's kick things off with Section 1, the invisible forces around us.
To truly wrap our heads around these forces, we first have to define the physical space where they actually operate, and that starts with the baseline concept of the electric circuit. An electric circuit isn't just some random jumble of wires, it's a highly specific, complete path through which electric charges can flow to provide energy. Think about it. If that path isn't complete, the invisible force goes nowhere. It's an all-or-nothing system.
Moving right along to Section 2, Anatomy of Electric Circuits.
Every single functional electric circuit out there basically needs 4 main components to work. First up, you've got a source, like a battery, to actually provide the electrical energy. Second, conducting wires, usually made of something like copper, to give that energy a designated path to travel. Third is the load. This could be a light bulb, a motor, whatever is consuming the energy to do the actual work. And finally, a switch, which acts as the gatekeeper, toggling the whole system between open and closed states.
That brings us to Section 3, Series versus Parallel Pathways.
Now this is where it gets really interesting. How you arrange those 4 components fundamentally changes how our invisible force behaves. In a series circuit, you've got only one continuous path for the current to follow, just a single loop. But in stark contrast, parallel circuits utilize multiple independent branching paths. The current actually divides itself and takes different routes all at the exact same time.
Imagine the physical difference this makes in the real world. If one single component fails or a wire gets cut in a series circuit, boom, it causes a total cascade failure. Everything goes dark because the only path is broken. But parallel circuits, they allow for totally independent operation. If one branch breaks, like a shattered light bulb, the other branches just keep on functioning perfectly because their distinct pathways back to the power source remain completely intact.
Okay, here is a massive cheat code for your exam. To remember the tricky resistance rules for these two circuits, just use a highway analogy. In a series circuit, adding components is like adding sequential toll booths on a single-lane road. Naturally, the total resistance increases, right? Traffic slows down. But in a parallel circuit, adding branches is like opening up extra lanes on that highway. Even though you're adding more stuff, the total resistance actually decreases because the cars, or the current, have more room to flow. Keep that little trick in your back pocket.
Let's shift gears now. Section 4, Cracking Electromagnetic Radiation.
So, electromagnetic radiation, or EMR, is absolutely mind-blowing because unlike a water wave or a sound wave, it can travel through a complete and total vacuum. It doesn't need a physical medium at all. It just blasts through space at the ultimate cosmic speed limit, the speed of light. That's 3.0 times 10 to the 8th meters per second. And it manages this by carrying energy via oscillating electric and magnetic fields that are perfectly perpendicular or orthogonal to each other. It's like a perfectly synchronized dance.
Depending on what physical medium it interacts with, this invisible radiation has 6 distinct behaviors. It might reflect, just bouncing back off a mirror. It can refract, meaning it bends as it enters a new medium, like a glass lens. It can diffract around corners, interfere with other waves, be completely absorbed by a dark material and turn into heat, or simply undergo transmission, passing straight through something transparent like a window pane.
Section 5, the complete EM spectrum.
I promised you some memorization tricks, and honestly, this one is gold.
To effortlessly memorize the exact order of the electromagnetic spectrum from lowest frequency to highest for your review, just memorize this beautifully absurd acronym, Red Martians Invade Venus Using X-ray Guns. That gives you radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma. Seriously, say it out loud 3 times right now, and you will literally never forget it.
When we look at the extremes of the spectrum, we see exactly how frequency dictates power. On the low end, we have the low-frequency giants. Radio waves have incredibly long wavelengths, which makes them safe enough to constantly pass right through our bodies to broadcast television signals. But on the exact opposite side, we have extreme high-frequency power. Gamma rays have such a short wavelength and high frequency that they carry enough raw energy to actually damage cellular tissue.
But right smack in the middle of these massive extremes is what we call the visible window. This tiny, tiny sliver of the spectrum, spanning from the longer red wavelengths down to the shorter violet ones, is literally the only portion of the entire electromagnetic spectrum that human eyes have evolved to naturally perceive. Everything else is completely invisible to us.
All right, final stretch. Section 6, Mastering the Universal Math.
Let's start with Ohm's law, V equals I times R. The absolute best way to picture this is with a water pipe analogy. Voltage, or V, is the pushing pressure from the pump. Current, or I, is the actual volume of the fluid flowing through, and resistance, or R, is the pinch restriction slowing that flow down. Think about it. If you pinch the pipe harder, resistance goes up, so the current has to go down, unless you massively increase the pressure to compensate.
Let's actually run the numbers with 3 quick examples. Step 1. Always write down your formula, V equals I times R. Example 1. If a basic flashlight has a current of 2 amps and a resistance of 3 ohms, just multiply them. Boom, you need 6 volts of pressure. Example 2. Actively rearranging the formula to compute current for a household appliance. If you know you have 120 volts at the wall and a resistance of 10 ohms, you divide V by R to get a current of 12 amps. And here's a third related example. What if you want to find the resistance for a toaster that's drawing 5 amps from a 120 volt outlet? Just divide 120 by 5, giving you a resistance of 24 ohms. Being able to confidently rearrange that triangle is huge. Now for the light math. Enter the wave equation, which basically acts like a mechanical seesaw. It states that the constant speed of light, represented by little c, equals frequency times wavelength. Because c never ever changes in a vacuum, frequency and wavelength operate on an inverse seesaw. If frequency goes up, wavelength absolutely must go down to keep the whole equation balanced.
Let's lock this in with 3 more examples. Example 1. Calculate the massive wavelength of a low-frequency radio broadcast. You divide the constant c by a low-frequency number, which results in a huge wavelength in meters. Example 2. Solve for a penetrating medical X-ray. Here, you divide c by an ultra-short wavelength, which gives you an astronomically high frequency. And for a third classic trick question example, what is the speed of a microwave compared to an X-ray in a vacuum? Trick question. It's exactly the same. The constant c, 3.0 times 10 to the 8th meters per second, never changes, regardless of the wave type.
And that brings us to the ultimate cheat sheet. This consolidates everything we've talked about, all the circuit diagnostics, the vital constants, the EM spectrum order, and the core equations you need. Honestly, pause the explainer right here and take a mental or literal screenshot for your final revision. It is all connected, and having it in one place is a total game changer.
We have covered a tremendous amount of ground today, but I want to leave you with this final thought. If these profound, seemingly magical, unseen forces of electricity and light are bound by such beautiful, rigid, and perfectly predictable mathematical rules, it really leaves you wondering, doesn't it? What other invisible mechanics of our vast universe are simply waiting out there right now for us to discover their underlying formulas? Keep questioning, keep studying, and I will see you in the next explainer.